Hello everyone, welcome to this introduction to exercise 10, distance to the Pleiades star cluster from astronomers as observers and experimenters, published by Kendall Hunt. I'm Professor Jeff Wilkerson at Luther College, and we're going to introduce you to this exercise that's a pretty standard technique, a good thing to practice for finding the distance to an open star cluster, or any star cluster, globular star cluster too, but a star cluster. It works because star clusters, the stars within a star cluster, are all about the same distance from us. The extent of a star cluster, if you have a star cluster out here, it has some linear extent, but that's very small relative to the distance that cluster is away from us always. We don't have any clusters that are close enough that that really makes a huge difference. The Pleiades would be one where it might make a slight difference, and we can walk you through that in the exercise to think about what difference it might make. But we're way out here someplace, so the distance to us isn't here or here or here. It's way over there in the next town compared to the size of the cluster typically. So all these stars can be taken to be the same distance from us. If they're taken to be the same distance from us, then that means the apparent magnitude gives us the same information, relative brightness of the stars wise, as the absolute magnitude. So we can make a graph called a color magnitude diagram of apparent magnitude, small m, as a function of color index or temperature or something like that. So B minus V in this case. Okay, the color index. And we're going to get a main sequence that pops out. So what we're doing here is a technique called main sequence fitting. And so we're going to get a main sequence of the Pleiades that pops out. Now you might find some stars have started to leave the main sequence up there, so be aware of that and pay attention to those stars and try to avoid using those stars in your fitting. You want to use only main sequence stars that are down in this region. And so you have an apparent magnitude that's associated with a given color this way. If we make this graph for absolute magnitude, for the zero-age main sequence, the main sequence that hasn't, where the stars haven't had time to evolve, and so they're right where they would be at zero age, we're going to get a graph that looks like this. If we align these two, we can see how these axes align, and you can see what small m, what apparent magnitude, aligns with what absolute magnitude, and that's going to give you a difference between absolute magnitude and apparent magnitude. And we can use the fact that d, the distance to the cluster, then is equal to 10 to the power of m minus m plus 5 over 5. Okay, so you can apparent magnitude minus absolute magnitude plus 5 over 5. That's your distance in parsecs. So in practice, the way we do this is there is a translucent overlay in the back. So you will plot the data from the cluster on this translucent sheet from the back of your lab book. And then you can plot the absolute main sequence, the absolute magnitude of the zero-age main sequence on here. And it says that a star of this color, suppose your main sequence looks like this. You pick a point, it says a star of 0.6 might have an absolute magnitude of 0.3. Okay? So you plot your main sequence on here, and it's going to tell you what absolute magnitude a star of a given color has. The data on here is going to tell you what apparent magnitude a star of that same color in the Pleiades has. And the difference between that apparent magnitude and absolute magnitude is going to give you the distance in parsecs. Now, the quick and easy way to do that is to plot a whole bunch of these points on here and to plot the points on here and align those main sequence. Slide this vertically, get the colors aligned. So you want to get the colors aligned so you can see the bottom axis, the bottom graph through the top. You see how the 0.9 is aligned with the 0.9 and the 1.2 is aligned with the 1.2. I don't know if you can see that on there or not. But you can see that, try to get that alignment. And then slide this scale vertically until your main sequence is aligned. Until you get this main sequence to align with this main sequence. Get the B minus V of the Pleiades lined up with the B minus V of the zero-age main sequence, slide it vertically until your two main sequences overlap, and then see how these scales. If we got this overlap at this point right here, I could look at that and say, I'm just guessing here, but I'm just saying, suppose those overlapped right there, then 6 aligned with 3, 5 aligned with 2, 4 aligned with 1, the difference is 3. m minus m right here. Small m minus big M. Apparent magnitude minus absolute magnitude would be 3. And you get a distance to the Pleiades that way. So that's a great way to do this exercise. Sticking this into this power, you better be pretty good about getting that alignment. So you better not round off too much. I just said 3, but you're better off saying, maybe it's 3.05. Even, try to guess an extra digit for what you can right there and see what you can do. You might try this a few times. You might try to just start over again. Stop, start over again, get the alignment of the two main sequences, and read it again and see what value you get the second time that you do that. When you go in and you align these things and measure the difference between apparent magnitude and absolute magnitude. Now, there's a different way to do this, and it's a more tedious way to do this, but it's going to give you some information about uncertainty if you want to get that information about uncertainty, if you're in a position to do that calculation of uncertainty. And so this different way to do that is to say, okay, every single data point that I have in this data set, let me find it. I've got the data set in here, and I've got the colors and magnitudes for the Pleiades, colors and magnitudes for the main sequence stars that are over here. I can, for every single point right here, I can calculate what the apparent magnitude is and what the color is right here. And I can go over here and I can say a star of that color. That's the best way to say that. Is a star of a given color right here has an absolute magnitude of what value over here. So for example, what I'm looking at right now says star number 35 has an apparent magnitude, has a color of 0.620. So star number 35 in the data set I'm looking at, it might be tweaked a little bit from what you have. Star 35 has an apparent color, M sub B minus M sub V, which is the same thing that I've called B minus V over there, I've lost it, 0.62 plus 0.620 is the color. Now I can come over here and say, what absolute magnitude would a star of 0.620 have? And it says 0.630 would be 4.76, and 0.43 would be 5. That's the temperature. I'm sorry. The absolute magnitude would be, if we go back this direction, 6.32 and of 0.63, and so that would be pretty close. We could just say the absolute magnitude is 6.32. Might be better to say, the star of 5.88 absolute magnitude is 0.43, and God grief, I'm looking at all of these completely wrong. Here's the way to do that. It says a star of 0.70 magnitude has a 0.70 color index, has an absolute magnitude of 5.38. 0.60 has an absolute magnitude of 4.79. You might extrapolate between those two to get your 0.62, 2/10 of the way from one to the other to estimate what the absolute magnitude is. Better way might be to go ahead and make your graph of absolute magnitude as a function of color, and then find your color down here, read it off your graph, and get what your absolute magnitude is. And then so you have an absolute magnitude and an apparent magnitude for each one, and you can stick it in and do a calculation, and you can get a distance. Okay? You can do that for every point in here. Let's back up and make sure that made sense. I stumbled over that just a little bit, so let's make sure that made sense for what you're doing. What I would recommend is maybe going ahead and making the graph of the data from table 2 that has the absolute magnitude up here and the color down here, and you make this graph of your main sequence of all the data that's in table 2. And then when you find a star, read every star that's in table 1, find its color, M sub B minus M sub V, find that on this horizontal axis, read up to your 0H main sequence, use a straight edge to line up across here and read off what the absolute magnitude is and calculate the distance. If you do that for every single star that's in this table, it's a much more tedious approach, but then you have you have a whole bunch, however many stars are in there, 20, 30, 40, 50 different measurements of the distance to that cluster. So you can take the mean of all of those values, and that mean is your best estimate of the distance to the Pleiades. The uncertainty, if you want to go through there, is going to be the standard deviation of that distribution divided by the square root of the number of trials that you did. So if you have 100 data points, the square root of 100 is 10. So you can calculate the standard deviation, put it in a computer program, and have the computer program calculate it for you. Put it in a calculator, have it calculate for you. Or you can work it out yourself if you want to do that. But you can say that the uncertainty is that, and so then you have the mean plus or minus the uncertainty is a good way to go about doing that. So the advantage of doing it point by point is that you can calculate, can average a lot of points, use a lot of data there to be able to measure the distance, to get a whole bunch of different distances, a whole bunch of different times, and then you can have a mechanism by which you can estimate what the uncertainty in that distance measurement is. And so you know, how good am I doing? What this approach to uncertainty measurement doesn't do for you is it doesn't account for bias or something. So suppose there's a lot of dust between us and the Pleiades, and it's scattering a lot of light out. You're going to overestimate the distance because the stars are going to look fainter than they would with that light being scattered out. This doesn't account for that at all. But it does account for your challenge in making these measurements. And so it gives you a good sense of what that uncertainty might be. It's a little more tedious. It's a little more calculationally involved than just aligning these axes and pulling these things off. But you have either approach, both approaches. Try them both and see how this works. I think is a great way to go. Once there's another part of this exercise that once you know the distance, you can use your S equals R theta relationship to determine what the linear size. You look at the apparent diameter of the cluster, the apparent angular diameter of the cluster on the sky, and calculate the actual linear dimension. How big across is the Pleiades cluster when we look at it? Is to say S equals R theta. R is what we just calculated as the distance right here in this exercise. So that's what we've got for you here. Comparing main sequence fitting. You're comparing stars on the main sequence. Here's the theory behind this whole thing. It's a great exercise because this is a really important technique for measuring distances and for understanding stars that way. Is to say stars that are on the main sequence. Now, stars that have evolved away from the main sequence, this doesn't work. But stars that are still on the main sequence, a star of a given color has a fixed absolute magnitude. Now, as the stars age, that changes just a little bit. There's not a zero width to the main sequence of a cluster, but it's okay for this approximation for where we're starting. That also doesn't show up in our uncertainty up there. But to say stars of a given color on the main sequence have a given absolute magnitude. If we compare our apparent magnitude to that absolute magnitude, we can determine the distance. And we can take a shortcut way by aligning these axes, or we can do it point by point for the individual points that we see up there and see what we get. But to say apparent magnitude, the stars look fainter if they're farther away. And so they're going to have a larger apparent magnitude. And they look brighter if they're closer. They're going to have a lower apparent magnitude. Comparing that apparent magnitude to the known absolute magnitude, it's known because we know the color, allows us to do a determination to the distance to any star cluster. Pleiades is a relatively close star cluster, which is a good one to do this for because there isn't a lot of material between us and the cluster that can affect our observation of that cluster. So this is a good exercise to get out there, practice a little bit of making main sequence, do a little bit of main sequence fitting. Good luck with it, everyone. We'll have more for you on other exercises.